Section 2.9, one-to-one functions and inverses. We've already learned that functions can't have two outputs for the same input. That would be like the vertical line test. But a one-to-one function is a special function that can't have two inputs produce the same output. So that would be like a horizontal line test. So parabolas are not one-to-one functions. This, which appears to be a square root function, is one-to-one. A cubic with a well-defined humps here is not one-to-one, but just a regular cubic can be one-to-one. So in some algebra terms, we could say that a function is one-to-one if f of x1 equals f of x2 only when x1 equals x2. So you get the same output only when the inputs were the same. So is x cubed one-to-one? So if you just look at the graph, x cubed looks kind of like that. We had a picture of it on the previous page, and that appears like the horizontal line test would pass. But also, if you just think about x cubed, there's no two values that we could plug in for x that will get the same output. If we plug in 1, we'd get 1, but if we plug in -1, we'd get -1. So yes, x cubed is one-to-one. How about x squared? Well, we know the graph of x squared looks like that, which would fail the horizontal line test, so no. But we can also think about it with numbers. If we plug in 1, 1 squared is 1. And if we plug in -1, -1 times -1 is also 1. So we get the same output from two different inputs. So it's not a function. Not a one-to-one function. How about the function 3x plus 4? Is that one-to-one? So for this, we're going to take a slightly different approach. We could just think about the graph. We know that that is a line which would definitely pass the horizontal line test. But for this one, let's go about it a little bit different. Let's take an algebraic approach, and we're going to plug in x1 and x2. We're going to start with assuming that f of x1 is the same as f of x2. So if we do that, that means 3 times x1 plus 4 equals 3 times x2 plus 4. So let's treat this as if it's an equation and try to solve for x1. So subtract 4 from each side. Those cancel out. Divide by 3 on each side. Those cancel out. We're left with x1 equals x2. And that's the original statement down here at the bottom of the first page. If f of x1 equals f of x2, that only happens when x1 equals x2. and that's exactly what we just showed. Started with f of x1 equals f of x2, and we showed that that only happens if x1 equals x2. So the same input is the only way to get two of the same output. So the inverse of a function, that comes naturally after talking about one-to-one, because only one-to-one functions have inverses. Only one-to-one functions have inverses. And an inverse is just a complete flip-flop of the function. The domains and ranges are flipped, the inputs and outputs are flopped. What that means is for the inverse function, f inverse of y equals x, that's the exact same thing as saying f of x equals y. The original f of x equals y means that we input x to get y, but for an inverse you would input y and get x back. So if we tie this back to composition of functions, if you were to compose f with f inverse of f just equals x, they would cancel out, because you would plug in one value, get its input to the, well, we'd start with f of x. So you plug in an x to get a y, but then you plug that y into the inverse to get x. And it could be the same thing no matter which way the composition occurs. So here's our function, a few values for it. F of 1 is 5, f of 3 is 7, f of 8 is negative 11. Then the inverses, or we're going to find the inverse from these values. So f inverse of 5, that's really saying what input would give 5 as an output. So refer back, here's 5 as an output, the input was 1. So f inverse of 5 is 1. 1 is what we would have to plug in to get 5. F inverse of 7, so that's saying what value gives us an output of 7 in the original function. So there's 7. 3 gives us that value, so f inverse of 7 equals 3. And then finally, f inverse of negative 10, so what input would give us negative 10 as an output? There's negative 10 for our output, and we got that with 8. So f inverse of negative 10 equals 8. It flips the x and y, the inputs and outputs. To verify that two functions are inverses, all we have to do is compose them together. So if f and g are inverses of each other, that means that so f of g of x is what we're going to look at. So let's plug g into f. So we're going to have x to the 1/3 to the third. You have a power to a power, you just multiply, so that would be x to the 3/3, which is just x, which is what would happen if these were inverses. Let's also do the other composition, g of f of x, to make sure. So now we're going to plug f into g. So now that's x to the 3rd to the 1/3. And again, power to a power, you multiply. X equals, or x to the 3/3, which is just x to the 1st. So when you do the composition, either way, you just get regular x. That means yes, they are inverses. We just showed it. So this is how you can find an inverse of a one-to-one function. Remember, only one-to-one functions have inverses. So first, to do it algebraically, replace f of x with y, then solve for x, then replace x with f inverse, and replace y with x. You can also do it if you're given a graph, because inverses are just reflections over the line y equals x, which would be this dashed line right here. So if you had the red original function, if you reflected that over the line y equals x, you can see it would still cross at the same points, but everything is reflected over. So let's start by finding a fairly easy inverse, 3x minus 2. So step 1 is replace f of x with y. Step 2, solve for x. So we're going to add 2 on both sides. Continue solving for x. Let's divide by 3. So we have x equals y plus 2 over 3. And then the final step was replace x with f inverse and replace y with x. There's our inverse function. Let's do another example. This one's a little bit more difficult. Same step, replace f of x with y. Now solve for x, so multiply by 2. Add 3 to both sides. And to get rid of the exponent of 5, we're going to do the 5th root. So that's our inverse. Let's just replace x with f inverse and replace y with x. There's the inverse. This time we're going to try to find the equation from the inverse from the graph. So the square root of x minus 2 could be the square root function shifted 2 to the right, so it's going to start here instead of the origin. And will look something like that. That's not very precise, but that's okay. Now to find the inverse, we're going to reflect it over the line y equals x. So reflect it over that dashed line that I just drew. So that would start here and go that direction. Everything reflected would go upward. And finally, to find the equation, we're going to go through those steps we just did a little bit ago. Replace f of x with y. And then solve for x, square both sides, and then add 2. Now you'll notice this isn't the complete parabola. So let's finish it off. F inverse x squared plus 2. It's not the complete parabola. It's only for x's are greater than 0, because our range of the original function, which becomes the new domain, was only x's are greater than 0. Since the original range is 0 to infinity, that becomes the new domain down here.